bad, right?
Right.
Doable.
Why were some of them like, where we had to do less than, or?
Why some of them they asked you to put it in interval notation versus inequality notation?
Yeah.
Just practice in the different methods. What you have to do. I will not be a stickler against that on the quiz class. No.
It sounds like it's the same thing, basically. It's just.
It is. The book's just trying to make sure that you're capable of transferring from one notation to the other.
Yeah, how good it is. It's like I kept messing with it. It's like, ugh.
Alright. Larry, where are you going? You gotta make it now. You good?
Yeah, he's good.
So, will you have anything that we have to like graph like
This?
yeah?
I don't believe.
Go check.
I don't believe I asked you to graph anything. The only thing that I can think that might be like that would be to, I may take that back for a moment.
Just graph the floors.
No, because what if the question is graph the function? I can't graph the
We
function.
haven't had to have the
The only things that I can think of that relate to graphing would be sort of describing the transformations of a graph in terms of the equation that you're given. For example, if I give you an equation, and I think this is on the quiz, right, Nicole? One of them says like f of x equals 1 over x, g of x is like x minus 4. And it says to do these compositions, f circle g of x, g circle f of x, and then describe the graphs in terms of transformation.
well, all of this not like too hard.
In this problem right here, if you understand what the graph looks like,
Yeah.
then you can easily identify what the transformations are.
Yeah.
But in the same way, you should be able to identify the transformations in terms of what the equations are as well.
If those are kind of the top problems, then okay.
Oh, well, okay. Well, I don't know what you find tough. What you find tough
Yeah.
might be easy to someone else. So that's
Those are easy.
okay. So if we do this, f circle g of x, what do we get? What's the equation for f circle g of x?
1 over x minus 4.
Okay, so 1 over x minus 4, right? And then what about g circle f of x? Yeah, there's that. Okay, so here we have two different functions. These are not equal, so let's not pretend they are. If I now ask you to describe what happened to the original graphs in each of these situations here, describe to me what the transformation for f circle g of x is telling us to do to our original graph. If we start with the original graph of 1 over x, what has this done to our graph of 1 over x? Moved it over 4. Now when you say over, I have to have a direction. Okay. This particular graph is the same as f of x minus 4. And this moves our graph to the right by 40. Okay. The g circle f of x, this one can be interpreted as g of x, oops, sorry. This is the same as f of x minus 4, right? That's what g circle f of x looks like. It's the function f of x minus 4. What has that done to our graph?
Yeah.
It shifted our graph of f of x down 4. And so, if the next question was to graph these, you're going to graph these now, you know what the transformation has done. Hopefully, you remember what the graph of 1 over x looks like. Knowing what the transformation are, knowing what 1 over x looks like, should be easy to graph these functions at this point. Okay? stretch before you came?
Compression.
Some compressions or what? Stretches and compressions again. Just identifying where the appropriate multiplication is taking place to identify how things are looking. One thing that I see a lot, and this is common because it's sort of backwards of what you think it is when dealing with multiplication on the inside. Suppose I look at a function like g of 4x. Okay. Now, in terms of transformations, what is this doing to the graph of g of x? What is this causing? Not necessarily. Come over here and I'll pick someone random. Nicole, what does this do to the graph? Okay, Jesus doesn't know. All right. That's all right. We'll come over here. Ben, did you say you knew what happened here? Stretching out. It actually is not stretching it out. It's actually compressing. When we multiply, and this is sort of where things are like backwards to what you think, right? Because you think, oh, I multiply on the inside by a big number, that should cause things to get wider, right? Because if I multiply a function on the outside by a big number, it causes it to get bigger too. It stretches it out vertically. But when we make changes on the inside, when we make changes to the inside of our function like this, it actually has the opposite effect of what we intuitively want to say happens. Okay? So in this case, this is actually a compression by a factor of 4. Okay? Everything that happened now happens in a much smaller range. Okay? That's what's going on with these multiplications on the inside like this. If I was to instead multiply by like a fourth or 4/10, something like this. Okay? Again, inside stuff is different than multiplying on the outside. When I multiply on the inside by something small, that actually causes my graph to have this stretching effect. Okay? This will actually stretch by a factor of 1/. Okay? It actually stretches our graph out like this.
Why is it
Because it doesn't really make sense to say it stretches by 0.4. It has to stretch by some amount.
They could go off of 1/4.
Would it be 1/4 or would it be 1/4?
Stretches by that much. Okay? Because what we're doing is we're making things happen 1/0.4 times as fast as they used to happen. Okay? So that's where that factor.
What's the equation?
I don't have an equation, it's just an arbitrary function. Okay. If I had a specific equation there, you may see it. For the problem, one of the problems that I often run into is that I put up functions that an inside change has a corresponding interpretation as a multiplication on the outside. If you want to see something maybe not so bad, take a look at, suppose g of x was the square root of x plus 2. Okay? Suppose you look at a function like that, and then you make these corresponding changes. Well, g of 4x would be 4x plus 2 square root. G of 0.4x, okay, that's square root of 0.4x plus 2. If you graph these functions, what you'll see is that these compressions and these stretches are observed when you make the graph come out. Okay? I won't draw the graph for these right now because I'm not a very good drawer. But if you take a look at those graphs, you should see the effects that these things are talking about. Okay. In terms of stretches and compressions, that's about all you need to know. I mean, you need to know what happens when I multiply on the inside by certain values, and then on the other hand, if I was to take 4 times g of x, okay, I should probably say horizontal. I apologize for that. Stretch horizontal. Okay. If I multiply on the outside changes affect what happens vertically. So 4 times g of x here, this is actually a stretch vertically. 4/10 as tall as it used to be.
Okay, that's what our compression is.
All right. Anything else?
No. He keeps asking me about
Domain. I do that too.
the domain of
I don't know how to do
range.
this problem. I'm gonna find someone like, he doesn't know how to do this problem. Someone get on board. What's up?
I don't know how to explain it to him.
Oh,
but
okay.
The domain
Yeah.
of range, like, if you have f of x equals 1 over x squared plus 1,
Okay.
x is greater than or equal to 0.
You want to find domain and range?
Yeah.
Okay. Domain and range of this function, or domain and range of like the inverse?
That function
Okay.
is compared to the inverse too.
Okay. The domain of this function is actually really easy because they tell you what the domain is. They tell you right there that x has to be greater than or equal to 0. Right? So there's our domain. Where? Domain. Bracket 0. Infinity. Okay. Range of this function. Now this is where we sort of have to sort of play this game of, okay, how do I find out what the range of this thing is? Well, the expression we're given is a fraction, right? We're given a function expressed as a fraction. So what I need to do is I need to try to figure out, okay, how big can this fraction possibly get? What's the largest possible value I can get out of this fraction? The largest value I get out of this fraction occurs when the denominator is the smallest, right? So I need to figure out where is x squared plus 1 as small as it can possibly be. Well, this is as small as possible when the x value is 0, right? The x squared is never going to be negative, so the smallest this occurs is when the x part here is 0. Well, what's the value I get out when x equals 0? I get out 1. So that means that this function can never, ever, 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 ever get bigger than 1. That's the largest value it can get to. Does it ever actually get to 1?
Yeah.
Sure it does. At x equals 0 it gets to 1, right? So it actually gets to 1. So, in our range, the right-hand side, 1 with a square bracket on it. Because I know that's the largest it can get, and I know it actually gets there. Alright, now what about the smallest value? Well, when is this fraction going to be as small as possible? The smallest this function gets is when the bottom is as large as possible. How large can the bottom get? You can get as big as I want it to be. When the bottom here is as big as it possibly could be, I have 1 divided by something that's really, really, really big. 1 divided by something really, really, really big is close to what value? 0. It's close to 0. Do I ever actually get 0 out? No. I don't get 0 out of this function because this thing can't ever be 0 unless the top is 0. So it doesn't actually equal 0, but it gets as close to 0 as I want it to. Okay? So there's our domain, and there's our range. Now you can ask, okay, what about the inverse function? Well, that's easy now, right? What's the domain of the inverse function? The domain of the inverse function is the range of the original function. So that's 0 to 1. And then our range must be